Hello everyone. So what we are going to discuss next in this mind map series is the rotational motion. First of all, we'll discuss about rotational motion. Why is it so different from the ones we have been discussing from the last chapters? In the last chapters, we always were concerned that let's this is some body and it has been thrown. It goes like this and maybe travels in a projectile. But we never discussed what if this body rotates. Why would the body rotate in the first place? For example, there is this block. Let's say you apply some force over here. It will accelerate. If it has a mass m, acceleration will be f by m. Let's say what I do is next, I apply the same exact force here, f. Now the acceleration will be 0 because net force is equal to 0. So what you're trying to say is if the net force on the body is 0, then there will be no acceleration, no movement. But what if there is this body, a pole, on which on this side you apply F and on this side you also apply F? Technically, if you look it from the previous chapters, the translation motions, then this is the same example as the previous one. Two equal forces acting in the opposite direction. So the body should not move. Okay. But obviously, from our observations in the real life, what we observe is this body actually starts to rotate, isn't it? So of course this motion is certainly different from the motion we have been discussing previously, which was um, translational. This type of motion is called rotational motion, in which the whole body rotates about some certain point. Let's say this is the point. If you have fixed this, imagine if you have fixed this into the ground or on the wall with a nail, and this can rotate, then this will just rotate like a blade of a helicopter, if you can imagine it. So that is rotational motion, and this is certainly a very new type of motion which will be discussing. And everything that is involved here, every variable, for example, in translation motion, we were mostly concerned about velocity, acceleration, things like that. We'll also have analogous terms here in the rotation motion, but they will be different. They will not be exactly the same as velocity and acceleration and things like that. First of all, the first part which will be different is the mass itself. Let's say there is this body of mass m, and you have to, let's say, there is this point, or you have held this point, and you want to rotate this body in a circular motion. All right. Now, the heavier the body, I'm calling this effort. All right. So, effort that you have to put to rotate the body will be directly proportional to m. The heavier the mass, the more you will apply the effort on it to rotate in a circular motion. But uh, let's say if this length is longer, what do you think? Would you need lesser effort to rotate the body in a circular motion, or you would need more effort? Of course, you will need more effort. So actually, it is also directly proportional to, if I call r, it is actually not r. It has been calculated numerically. It has been found that it is directly proportional to r square. From here, what we call is uh, I may say that this is uh, rotational inertia. Rotational inertia. What was inertia? The inertia in translation motion was actually the resistance of the body to move or from moving. That was numerically equal to the mass. But the term I'm defining here, I have called this some layman term, which is rotational inertia, just so that you understand what he's talking about. So it will be directly proportional to m and r square. It is actually defined as mr square only. And the formal name for this rotational inertia is called moment of inertia. Moment of inertia. This is mr square, and that is the moment of inertia, which actually defines what is the resistance of the body it will provide when it is about to be rotated along about a fixed axis, which is this one, the fixed axis. All right. Now, the key thing that I'm talking about here is, for everything rotational or translation, let's say I'm talking about translational world, which we were talking about in the previous chapters, and this is rotational world. I will list the analogous terms. First of all, what we discussed here was, in here mass or inertia was there, and here it is moment of inertia. In the translational motion we always had velocity, but here we have angular velocity. I will define what it is. I'm just listing them right now. Angular velocity, maybe acceleration, angular acceleration, angular acceleration, maybe force. This is called moment of force, moment of force, also called as torque. All right. And maybe I think I can define all one more thing, momentum. It is called angular momentum here, angular. If I ever find a term which is something in the order of moment of xyz, moment of some xyz term, you will immediately draw analogy in this table, that whatever xyz is there, you just have to cross check here. Whatever xyz, if I say moment of acceleration, you will switch to the angular acceleration there. Moment of something is the way that you put a variable from the translational motion into the rotational world. All right. So I hope this was clear. I have already discussed this one. Let's discuss the velocity. Of course, we will be discussing this in more detail in the later part. But let me just give you the idea of angular velocity. You already know what is velocity, angular velocity. Let's say there is this circular motion in which there is this particle. All right, there is this particle. Now, how do we define velocity? It is defined as, let's say it has covered some distance dr over some theta angle dr, and having radius r. So if I calculate dr by dt, it gives me velocity. But do you know what is or let me just define it, what it is. So how we define angular velocity is, it is the rate of change of angle. Let's say I give it 1 second, and the angle through which it rotates, the angle which it makes from the initial position to the final position, let's say it is pi angle. So the angular frequency or angular velocity will be equal to pi radians per second, since the angle is always calculated in radians, SI in it. Now, when you have the angular velocity, let me just quickly give you the relation between the angular velocity and the translation velocity. Let's say from here to here, some displacement has occurred, which is dr, small dr, very small displacement, and the small angle theta has been covered. Now, can I write v is equal to dr by dt? Of course, it is the way velocity is defined. Now, I divide this by r and multiply this by r. Can I take this term and leave the rest? Dr by r into r over dt. Now, can I say this dr is nothing but d theta? This dr is nothing but d theta into r. Why? Because for any sector, the length of the sector, if this is theta, the length of the sector is r theta. If I have taken d theta, and if it is a very small distance, the length of the sector is almost a straight line, which I have taken dr, the displacement. All right. So when you do dr by r, which is nothing but dr is equal to r d theta by r into r by dt. So r gets cancelled out, and you're left with d theta by dt plus r. All right. This is sorry, plus, not plus. This is multiplied. Now, what is this d theta by dt? That is the one that I explained earlier, that the rate of change of angle is nothing but angular velocity. It means v is equal to omega r is the relation between angular velocity and translational velocity of the particle. The velocity it will have here in this direction, and the angular velocity the particle will have omega. This is the relation. All right. So this was the angular velocity. In the same manner, we can define acceleration and the angular acceleration. Acceleration was defined as dv by dt, rate of change of velocity or the change in velocity per unit time. This is acceleration. In the same manner, angular acceleration alpha is defined as rate of change of angular velocity or the change in angular velocity per unit time. This is called angular acceleration. This is angular acceleration. And the moment of force, what is the moment of force? Maybe we will come back later on it, a few moments after this. Or should I define it here itself? Maybe yes, because I think it is not in the mind map. Uh, yes, I think it is not. So let me just define here itself. What is torque? Let me quickly give you an example. Let's say there is this door which has these two hinges, and you want to open the door. You will most probably push in this direction or push the door in this direction so that it rotates. But whenever you push the door, you make sure that you are as close to this end while pushing it. When you close, let's say at this point, or when you push at this point, it is very difficult for the door to close. Why? If you are applying the same force here, then the same effect should happen. But this is not the realm of translation. This is the realm of rotation. Here, force itself will not do anything. There should be another thing which is called moment of force or torque, which is actually driving the acceleration or the angular acceleration here. Torque is defined as r cross f, where r is the distance from the hinge or the axis of rotation. This is the axis of rotation, right? The axis around which the whole body is going to rotate. So this is the distance r, and this is the force. And why I have applied cross here? Cross is the cross product. It means for the maximum torque, the angle between r and f should be 90-degree, right? Because when you find the magnitude of cross products, then it is r f sine theta. All right. So this is called torque or the moment of force. It is both proportional on the force which is applied and the distance from the axis of rotation. All right. So this was the moment of force or the torque and moment of sorry, angular momentum. All right, angular momentum. First of all, there was this let's say there was this ball of mass m and going in this direction v. All right. Now we clearly see that the momentum is defined as mv. No question about that. But let's say the ball is a part of a rod which is actually rotating on on this axis. the axis going into the plane. Then the distance from the axis of rotation is r. Then angular momentum, which is denoted by the term L, it is defined as, in the same manner, r cross p. All right, or you can say this is r cross, or maybe m r cross v. All right, this is the angular momentum of the body. Of course, this is a cross product again, so you will have to take care of the angle between them, sine theta. Now, which parts has been dealt with is, I guess, moment of inertia. I will go in detail. So I've just given you the basics of rotational motion because it is very important to understand why we are doing all this or studying all these. Now, let's get into the moment of inertia. Let's say there is this axis of rotation and there is this particle which is moving in a circular orbit having some radius r from the axis of rotation. Then of course, how we defined moment of inertia is equal to m r square for a one particular particle system, as simple as that. But let's say there are two particles, m1 and m2, having radius r1 and r2, right? So remember what I talked about in the moment of inertia. It is the resistance which the body or the system of body provides or exerts so that it is able to resist the circular motion or the rotational motion. So the higher the moment of inertia, the higher it will resist. The resistances in this part should add up, right? If you have more than one system of bodies, then the resistances or the moment of inertia should add up. So of the body in this case will be equal to m1 r1 square plus m2 r2 square. This is the fundamental on which you will be calculating or you will be deriving the moment of inertia of so many diverse type of things. For example, if you have a uniform rod of mass m and length l, the obvious thing could be the rotation of the body at the midpoint. All right, so this will be rotating here like this. In this part, the moment of inertia of the rod is equal to m l square by 12. All right, now another example could be, let's say there is this ring. Now the ring can be viewed as small masses which are rotating at a same distance r, right? So in this case, can I say moment of inertia is nothing but I1 plus I2 plus I3, all that, and in that m1 into r square plus m2 into r square. M1 and m2 are the distance of these small elements, and when you take the r square in common, it becomes m1 plus m2 plus all that masses, and when you add up the masses of all these elements, you get the mass of the ring. So that's why the moment of inertia for a ring is nothing but m r square, as simple as that. So I for a ring is equal to m r square, and actually you will derive later. If you have a disk, and you want to rotate it on the axis of rotation which is pointing towards or inside the board, in that case of a disk is equal to m r square by 2. We can take up even more examples. Let's say there is this sphere, then moment of inertia of the sphere about any of the radii, or sorry, diameters, sphere is actually equal to 2 by 5 mr square. Now, there are two different theorems in the calculation of moment of inertia, which will help us in deriving lots of geographical bodies on which you can calculate the moment of inertia. The first one is called parallel axis theorem, axis theorem, and the second one is called perpendicular axis theorem, axis theorem. All right. Now, the parallel axis theorem, theorem says that if you have, let's say, there is this body and having the center of mass at this particular point. Center of mass, I think we already discussed that. Uh, Maybe we can take up it later, small after this part. What is exactly the center of mass and how it is calculated? But for this point, you can take it up that this rule applies to the center of mass of the body. There is this particular point on which you can assume the whole body to be to be at a point mass that is called the center of mass. We will take it up later. But let's say there is this axis of rotation I, and there is another axis of rotation which is parallel to the original axis of theorem, or sorry, original axis of rotation, which is passing through the center of mass, and this one doesn't pass through it. Let's say the distance between them is d. All right. Now, the parallel axis theorem says that if you have to calculate the new axis, new moment of inertia, it will be equal to the original moment of inertia plus m d square, where m is the whole mass of the body. This is called the parallel axis theorem. Now, there is this particular restriction that you have to follow, that this I should always pass through, or this moment of inertia which we are talking about, the axis of rotation of that moment of inertia should pass through the center of mass. It is essential. If it does not pass through the center of mass, you cannot apply the parallel axis theorem. In the same manner, we have something called perpendicular axis theorem, and there is this restriction about this, that it is applicable only to 2D bodies, or laminar bodies we call it. 2D means a sheet. It could be of any shape, it doesn't matter, but it has to be a sheet. It should not have any length in the third dimension. In those cases, let's say there is this axis of rotation in the x-axis, there is this axis of rotation in the y-axis, then there is this another axis of rotation which is in the z-axis, which is going inside the plane. Then, since it is in the x and y direction, the whole planar stuff that we have is in the xy plane. Then the moment of inertia, which is perpendicular to the plane of the body, should be equal to ix plus iy. This is the perpendicular axis theorem, and of course you have to remember the restrictions which are most important, otherwise you will apply the wrong theorem in the wrong place. So these were the two theorems for calculation of moment of inertia. All right, so we have already dealt with it, this one as well, and I think I already gave you this one, ring one, and disk and sphere. We will get these ones on the basis of the theorems. For example, there is this rod which rotates around this axis, having length L and mass M. There's of course around this axis, which passes through the center of mass or the center of the body. It is equal to ml square by 12. Now, if you have to find the moment of inertia along this axis of rotation, which is of course having L by 2 distance, then this I dash will be equal to, what should we apply here? Of course, we should apply the parallel axis theorem, because this axis and this axis are parallel and one of them lies on the center of mass. So this ICM, center of mass, plus M d square. So what was that? ML square by 12 plus M L square by 4. When you calculate all this, it comes out to be ml square by 3. This is the moment of inertia for a rod hinged from the one of the sides, or uh, one of the end points. All right. In the same manner, let's say you have a ring and you want to find the moment of inertia about this axis, which is in the same plane as the plane of the ring. Then what we do is we imagine another axis which is actually the same as the previous one, which is the diameter. This is Ix and this is Iy, and of course you know the moment of inertia which is Iz going inside the plane, which is mr square for the ring. Then I dash or Ix plus Iy should be equal to mr square. But if you closely observe this, then there is no actually practical difference between Ix and Iy, since it is a symmetrical body. So this means 2Ix is equal to mr square. Ix is equal to mr square by 2. In the same manner, you can find out for a disk, which will come out to be Ix is equal to mr square by 4, because it will again be the same Ix and Iy. So you can add them up and equate it to the Iz. So if this is clear, I think this whole part is okay. Now there is this radius of gyration or gyration, whatever you pronounce it. There is this simple thing about the radius of gyration is that, let's say there is this body having moment of inertia is equal to whatever it is, I. Moment of inertia is equal to I. Then what this actually wants me to assume is, what if there is another system in which from the axis of rotation there is another mass m which is having the same mass as the original body, but having some distance k, such that the moment of inertia in this case is equal to the moment of inertia in this case. What if this was the situation? Then the k what we got from here is actually called the radius of gyration. It is that distance from the axis of rotation around which, if you assume even a point mass, then the moment of inertia should not change, basically. Radius of gyration. Now if you how to calculate it? Let's say there is this moment of inertia I. It should be equal to the moment of inertia of this system. And what's the moment of inertia of this system? Since it is rotating around the axis with a radius k, then it should be k square mk square, right? Mk square. And how you find the radius of gyration? It will be simply k is equal to I by m, the whole under root, nothing else. For example, if you have a ring, or sorry, maybe a disk, because a ring will be very simple example. A disk having this axis of rotation, then in that case the radius of gyration should be, what is the moment of inertia of that disk? Mr square by 2 inside the plane divided by the mass itself. So that will be equal to r by root 2. This is the radius of gyration of a disk about the axis of rotation passing into the plane of the disk. I hope that was okay. That is the radius of gyration, which is I by m, and in this way you can find the radius of gyration. Rigid body is that it is just a theoretical concept that, let's say there is this body in which there are 2 points, 1 and 2, maybe there are many points. Then if a body rotates or it translates, if the distance between these 2 points, distance between 1 and 2, doesn't change with the rotation or translation of the body, then that type of body is called rigid body. You can it should be applicable to all the combination of all different particles inside the system. Now, center of mass, I think that should be the next thing which we should cover. It is very important. See, center of mass, right? Now, let's say there is this body of, or maybe do I have something here? Let's say there is this of pen of length r. At a certain distance, it can be almost balanced, right? It means if the gravity is acting in this direction or the normal force is acting in this direction, then the rotational or the torque on this side and torque on that side is exactly balancing each other out, and this point will be called the center of gravity in this case, which actually matches with the center of mass. If you don't have a variable uh, gravitational force, which is not there actually in most of the cases for practical purposes. Now, how do we calculate center of mass of a body? Let's say there are two bodies having equal mass. Then we always say that the middle point between them will act as the center of mass. Of course, because it is at the center for two equal bodies. But what if it is having 2m mass and this one has a small m mass? Should it be exactly at the same middle point? Of course not, because a heavier mass is on this side. The center of mass should also lie at a point which is closer to the heavier mass. How do we calculate the center of mass? Let's say there is a system of n number of particles, and we are in a Cartesian plane. All right. Let's say there is this x1, y1, x2, y2. These are the coordinates. Then the center of mass can be calculated as, let's say you want to find the center of mass along the x direction. Then x center of mass is equal to, or you want to find the x coordinate of the center of mass, then x center of mass should be equal to m1 x1 plus m2 x2 plus m3 x3, and so on, in the same fashion for all the particles. Divide by m1 plus m2 plus m3 plus all the masses. This is the formula for calculating center of mass of any body in any axis. If you want to find in this the y coordinate, you just have to plug the same things, m1 y1 plus m2 y2 plus m3 y3, in the same manner till the last point, m1 plus m2 plus all the masses. This will give me the center of mass, the coordinate of center of mass in the y direction. In the same manner you can do for the z direction as well for 3D systems. So this was center of mass. All right. Now, if you want to find the velocity of center of mass, then all we have to do is probably do d by dt, d by dt, and since this is a constant, it will come out the denominator, and it will leave me to something in the manner of m1 dx1 by dt plus m2 dx2 by dt, and in the same fashion divide by m1 plus m2 plus m3, all that. What is this? It is nothing but the velocity of x1 particle. This is the velocity of x2 particle in the x direction. So it means m1 v1 plus m2 v2 plus all that plus m1 plus m2 plus, this should be the velocity of center of mass. All right, this should be the velocity of center of mass of the particles. So this was about the center of mass, which is very important. And in the same manner, I can calculate the acceleration, because if I have this equation for the velocity, I can again differentiate it with respect to time, and I will have the acceleration of center of mass, and all these will give me accelerations. So the acceleration of center of mass will become in m1 a1 plus m2 a2 plus m3 a3, and of course all these are vectors. Do not forget about this. All these are vectors. m1 plus m2 plus m3, all of that. So this is how you calculate either the position of center of mass, the velocity of center of mass, or the acceleration of center of mass. All right. Let's just check which part of the mind map we have covered. I think these has been covered. Now, the thing that I talked about is position of center of mass of an object changes in the translation motion but remains unchanged. Yes, this is the thing with which we started this chapter actually. The example that I gave you for the rotation in the translation motion, this actually changes, right? The position of the center of mass changes. This is called pure translation. And there could be another type of motion in which it is just rotating. It is not move. It is not translating. The center of mass remains static, and the whole body rotates around the center of mass. Of course, the all the particles will have individual velocities. For example, if you want to find the velocity of this one, this will be simply omega into r1, where r1 is the distance between the center of mass or the axis of rotation and that particle itself. But if you talk about the velocity of this point, the center of mass, it should remain 0. So in this pure rotation, this is called pure rotation, in which the center of mass will remain static, and this is pure translation, in which there will be no rotation, only the translation of the center of mass. But there is another thing called mixed rotation and translation. There can be another case, translation plus rotation. For example, if you look at a cricket ball, the ball is delivered, it is undergoing a projectile motion, but at the same time it is spinning around its axis, right? So that is a example of translation as well as rotation. This has been covered then. Now, any other thing? Yes, I think the very important part which has been left is angular momentum. I think I have covered, but still I would just visit it again and talk again. I will visit. No, but this is the very important part for this chapter. In the Newton's or the equations of motion that we had learned in kinematics, equations of motion, what were the three equations of motion? V is equal to u plus at, s is equal to ut plus half at square, and v square minus u square is equal to 2as. As simple as that. All right. Now what you have to do is, we'll use the table which I had generated. I think it was here. Where is it? Yes. For mass, you replace with moment of inertia. For velocity, you replace with angular velocity. For acceleration, you replace with angular acceleration. And you have the all the equations for the translation valid for the rotation as well. For example, if you replace what is this initial, sorry, final velocity, right? So final angular velocity will be equal to initial angular velocity plus what I have to replace with the acceleration here, angular acceleration, since we are in the realm of rotation, alpha t. This is the first equation of motion. In the same fashion, I can write the second equation of motion. This was the displacement. In this case, it will be the change in the angle, delta theta. It will be equal to, you replace it with the omega I into t plus half into alpha t square. This is the second equation of motion. And the final equation of motion will be omega final square minus omega initial square is equal to 2 into, what is this, acceleration, right? So I will replace it with angular acceleration, and this is the displacement, delta theta. This will be the third equation of motion. So it is very easy to remember. Even if you don't actually remember all of these, you can simply write them and replace with the analogous term, and you have it there. All right. So these were the, many times it is also written as theta, but to be very accurate, it should be written as delta theta, because it is the change in angle covered. It is not the original angle. All right. Now, uh, let me just talk about the torque and the angular momentum for a while, and then we will be mostly done with this one. Let's say, and I think in the mind map there is one part which has been left out, which is energy related to the rotating bodies. I will deal with it, no problem. First we take the torque. How do we define torque? Torque is the analogous of force, analog of force in the rotational world. How do we define torque? It is represented with the term tau, which is a Greek letter, r cross f. All right. Now, if you have two vectors with a cross between them, cross product, it is nothing but rf sine theta n cap, where n cap is the direction which is perpendicular to both r and f, and you have the torque there. All right. The second thing we wanted to discuss was the angular momentum. Angular momentum. What is this analog of? It is angular analog of simple momentum or translational momentum. This could be, so omega is equal to r cross p, and the same thing I can do it here, rp sine theta n cap. Sorry, this is angular momentum. This is angular momentum. So angular momentum is here. Now, in the translational world, did we have a relation between force and momentum? Of course we had. Force was equal to the rate of change of momentum, nothing else. Right? Now, what we have here is omega, sorry, tau. What is tau? R cross F, right? I can say that this is nothing but R cross dp by dt. All right. Now, tau is equal to I can definitely write it as in cross dp by dt. What is this term? R cross dp, change in particular momentum, R cross that momentum. It gives you angular momentum, right? So the rate of change of angular momentum will give me torque. It is the simple law. All right, no problem in this one. Meanwhile, I think we should discuss also about the, and of course there's this one thing called is equal to I alpha. How does it come up? Because we had this analogous equation F is equal to ma. When you replace force, then you have tau, which is the angular sorry, moment of force or the torque. M, the analog, is I, and the analog of acceleration is alpha. This is just for remembering. It will be very useful. But one thing which was missed in the mind map was about the energy associated with the rotating bodies. Now, let's say there is this body which is rotating. All right, this body which is rotating at some angular velocity omega. Okay. Now, let's say there is this particle having some small mass or small mass m1 having the same rotation omega, right? What's the velocity it will have? It will have a velocity which is at a distance r1, then it will have a velocity of omega r1. In the same manner, everything will have similar velocities. Now, if I want to find out the energy here, the kinetic energy, it will be equal to half m v square for each of the particle. And if I want to find the total kinetic energy related to the rotation, it will be equal to the summation of half m I v I square, right? And if you do that, half comes out outside and you have mi. And can you replace vi with respect to I omega into ri? Omega into ri, because omega is going to be constant, the rate of change of angle, ri square. What I have over here is omega. Since this one is a constant, it can quickly come out omega square, and you have this summation of mi ri square. Mr square, the summation of all the bodies, mr square, it is nothing but the total moment of inertia, right? So it means kinetic energy rotation is nothing but half I omega square. This is the energy associated with pure rotation. But let's say you have something called a body which is rotating as well as translating. In that case, the total kinetic energy will be actually equal to half m into vcm whole square, the center of mass, the velocity of the center of mass, plus half I omega square. This is going to the total energy, because this is for the translation motion, and this is for the rotation motion. Since the body is doing both types of motion, then of course this thing, the translation the energy related with the translation is independent of the energy related with the rotation, right? Of course. Now, for example, if I have some body rotating with omega, as well as the center of mass is going here with a velocity v, then using this formula you can quickly find out the kinetic energy. All right, now let me just check if I have missed something in this mind map. I think most of it has been covered, and this is the reason why we calculated the center of mass in the first place. The whole exercise of doing the center of mass was because in the end you will have to use the center of mass in different type of mixed uh, mixed motions in which both translation and rotation are there, of course. Okay, so I hope this was clear. Let me just check whether I have something which I told I will be discussing later. And of course, the this thing can be derived in the same fashion as the how we derived F is equal to ma. How do we derive F is equal to ma? Because we define that force is equal to the rate of change of momentum, right? dp by dt, and you have dp is equal to dmv dt, and F is equal to ma from here. Since the m comes out and dv by dt is equal to ma, sorry, acceleration. In the same fashion, I have already told you that omega is, sorry, tau is equal to the rate of change of angular velocity, right? That's a simple thing. What we can do here is, what is the angular velocity? First of all, it is nothing but um, how do we define angular velocity? Angular velocity is nothing but I omega, right? So d I omega by dt, and since I is a constant, it is the moment of inertia which is going to be constant, analog of mass. So I comes out, and this is d omega by dt. So let me just erase this one. Yes, and hence you have I, and the rate of change of omega, or the rate of change of angular velocity, is nothing but acceleration. This is how you get the analog of F is equal to ma in the realm of rotation. Okay. The reason why I'm doing all these small derivations is because even if you don't remember, it will be helpful. Or in certain questions, it is often uh, more helpful to use the derivatory part rather than using the whole equation is as it is. Okay, so I think that is enough for today. The, I hope the mind map was clear to you. Thank you.